Welcome back, guys. Before we dive into the subject of adding, subtracting, multiplying, and dividing with what are known as fractions or quotients, we need to talk about a number of properties that numbers possess that are really, really critical to being able to manipulate fractions. And that is, we're going to need to talk about what is known as factorization and finding the greatest common factor, or the GCF. So let's just start off by introducing a definition. A factor is a number which divides another number evenly. So we would say a number which divides another number evenly is a factor. And providing an example of a factor is pretty easy. Suppose you have a number like 6, and you take 6, and we know that 6 can be divided by 3. 6 divided by 3 gives you 2. And what this tells you is that 3 is a factor of 6. Another example, if we have 8 and divided by 2, we know that 8 divided by 2 gives you 4. So we would say that 4 is a factor of 8. Pretty straightforward. So if a number divides another number evenly, we say that that number is a factor. Now, critically important to know is that there are special factors called prime factors that are really, really super important to simplifying fractions. But before we get to that, let's just review what a prime number is. So a prime number is any number which can only be divided by itself and 1. That is a prime number. So any number which can only be divided evenly, I should say evenly, by itself and 1 is a prime number. Because you can divide it by other numbers, it just won't be divisible evenly. So an example of this is 3. 3 can divide by 3 evenly, and that gives you 1. And you can take 3 and you can divide it by 1, and that gives you 3. But if I try to take 3 and divide it by any other number, it's not going to work out so well. Another way of defining a prime number is you say that it is a number which is composed only of trivial factors. So any number which only possesses trivial factors is prime. So when I say the word trivial in a math context, what trivial usually means is it means useless. Meaning that whenever you perform an operation or do something in order to find some sort of information, and what is produced is meaningless or useless, we would say that that operation is trivial. And so for prime numbers, what's so special is this idea that the only types of factors that a prime number possesses are trivial or otherwise useless factors. It's not that they don't have factors, it's just that they're trivial and we wouldn't otherwise denote them with the exception of this particular case. Okay, so why is it important to know about prime numbers? Well, it turns out that finding the GCF technique can often be done by decomposing a number into what are known as its prime factors. Now, fact that you should know, this is a fact. This is a fact with respect to division. All numbers are composed of a product of prime factors. Now, I can't go into a proof of this because the proof itself would take a lot of time, and that would be somewhat above the scope of this particular lesson. But I can give you some arguments for why this statement is true. But first of all, let's understand the statement itself. All numbers are composed of a product of prime factors. Okay, composed just is a word that means built of or built from. So you could use the phrase built from or built of instead of composed. So numbers themselves are generally built of or built from a product meaning if you take numbers and multiply them together, and what kinds of numbers are we multiplying together? We're multiplying a sequence of prime factors. So let's see how that's the case. Consider the number 6. I hope everybody agrees that 6 is the same thing as 3 times 2. Well, 3 is prime because the only number that divides 3 is 3 and 1, and 2 is also prime. If we look at the number 8, 8 is the same thing as 4 times 2. And of course, 4 is the same thing as 2 times 2. So here we are. Here are some prime factors. Another definition, prime factorization. When a number is decomposed, which is the opposite of composed, so it is broken down, when a number is broken down into a sequence of prime factors that are multiplied together, we call that prime factorization. Call this process or the result prime factorization. So the process by which you determine that 8 can be decomposed into a sequence of 2's that are multiplied together, i.e. 2 times 2 times 2, or the process that you use to determine that 6 can be decomposed into 3 times 2, we call that the prime factorization of 6 and 8, respectively. Okay, so, but the long and the short is every single number on the number line can be decomposed, even if trivially, into some sort of a prime factorization. And this is useful for when we need to find the GCF of a number. So real quick, let's just list out some of the prime numbers that you might encounter on the homework. So the first prime is trivially 1, because obviously 1 only divides by itself. So it's just 1 divided by 1 is 1, right? But then 2 is the next prime number because 2 only divides by 2 and 1. So just by definition, 2 is prime. But interestingly, 2 is also the only even number that is prime. And this is pretty easy to prove if you consider that all other even numbers are simply a multiple of 2. So given that all other numbers are a multiple of 2, there can be no other number that is even, by definition, that is prime. Okay? So 2 will be the only prime number on the number line. The next prime number is 3. And then we start seeing that prime numbers kind of space out. So you go from 3 to 5, from 5 goes to 7, from 7 to 11, and you get to 13. You jump, you get to 17, 19, 23, 31, 43. I think 53 is prime. Could be wrong, but I think it's prime. So on and so forth. So those would be some of the prime numbers as you're going along up to 100. Now, luckily for a lot of students, if the textbook asks you to decompose a number into its prime factorization, you guys are really only going to have to check up to maybe 19, maybe 19. I've never seen a question on the online homework that asks you to decompose a number into a prime factor that is greater than 19. Okay, and I'll eat a boot if that is in fact the case, but I don't think I'm wrong. So at any rate, okay. Usually when we take a number and we list out its prime factorization, we can do so using what is called a factorization diagram. So if you take a number such as 48 and you want to locate all of the prime factors of 48, then what we're going to do is we're going to kind of make a diagram that looks a little bit like a tree. We're going to draw these two lines that are sticking off to the right and to the left at a diagonal. And what we'll do is we'll try to find a number that divides evenly into 48. Since I picked a number that is even, and I said that all even numbers are divisible by 2 at a certain point in this year, we can go ahead and take 48 and we'll divide it by 2. 2 goes into 4 2 times. 2 times 2 is 4. Subtract, you get 0. Drop your 8 down. 2 goes into 8 4 times. 4 times 2 is 8. Subtract, you get 0. All right. So what did this tell us? This tells us that 2 and 24 multiplies together to be 48. Now, what we're going to do is we're going to keep going with this. We're going to keep looking at these numbers until we can no longer divide by anything other than trivial factors, okay? So if we look at this 2, since 2 is prime, there's really nothing we can do. The only thing that divides 2 is 1 and 2, and that's not going to help us for this factor diagram, because the only thing that we want to list out with the factor tree diagram is we want to list out the prime factors to begin with. So once we find a prime factor, we should stop. But if you look at the 24, 24 will be divisible by 2. 2 times 12 gives you 24. And if I divide 12, 2 times 6 gives me 12. And if I take 6, 2 times 3 gives me 6. And so this is my factor tree diagram. I find it immensely helpful to write out these factor tree diagrams. Okay. Now, once you have your factor tree diagram, you can list out the prime numbers as being multiplied in series with each other. So 2 is multiplied with 2 is multiplied with 2 is multiplied with 2 is multiplied with 3, and that gives you 48. It's pretty straightforward. Now, when it comes to finding a GCF, we're going to take this idea of using a factor tree diagram, and what it'll allow us to do is it will allow us to find all of the prime factors of a given number. Then we're going to use those prime factors to critically locate what is known as the greatest common factor, or the GCF. So a little bit of a definition, I guess, before we get to calculating the GCF of something. Let's just define the GCF. The GCF, or the greatest common factor, is just the largest number which is divisible into 2 or more quantities. It turns out that locating the GCF is critical to being able to add or subtract and or simplify fractions in many instances. So we're going to be using the GCF technique a lot whenever we get to these concepts. So go ahead and make a note down here at the bottom, used for adding, subtracting fractions, as well as simplifying fractions. We'll talk about what that means, but for now, we're just learning the technique. All right, so the greatest common factor is the largest number, which is divisible into two or more quantities. So what this means is, let's just give you an example. Suppose I want to calculate 55, the GCF of 55 and 45. What we do with the greatest common factor technique is we're going to list out the prime factors of both of these numbers. We're going to create a factor tree diagram for both of these numbers. And for 45, 45 is divisible by 5 and 9, because 5 times 9 gives you 45. And then 5 is prime, so we don't have to do anything with that number, but 9 decomposes into 3 and 3. Meanwhile, 55 is the same thing as 5 times 11. All right. So if you look to these factor tree diagrams, you'll note that you have a common factor. 5 is, in fact, a common factor between 45 and 55. And because it is the largest common factor, it's the only common factor, in fact, we would say it is the greatest common factor. Now, in many instances, finding the GCF will not be as simple as simply writing out the factor tree diagram. In some cases it is, but in many instances it's not. And so we kind of have developed a technique over the years that utilizes prime factors in order to locate the GCF every single time. So the long and the short of it is, instead of relying on a factor tree diagram, what we are going to do is we are going to list out the prime factors of the numbers in question. In this case, we want to find the prime factorization of 55 and 45. So we're going to list out the prime factors. 55 is 5 times 11. 45 is the same thing as 5 times 3 times 3. And what we're going to use that prime factorization for is it's going to allow us to calculate the GCF by simply looking at the factors. In this case, you will cross out any factors that are in common and simply write them once as a sequence of products with each other. And so in this case, because we have a 5 in common, and really that's the only item that is in common between these two numbers, we would cross out the 5 and simply write a 5 as our GCF. Okay, but suppose we had a more complicated number. Suppose we had, say, a GCF that was something like 180 and 150. What's going to happen is you will have to decompose these numbers into a sequence of prime factors. For 180, we could guess that 2 is divisible into 180. We could say 2 into 180. 2 goes into 18 9 times. 9 times 2 gives you 18. Subtract, you get 0. Drop your 0 down. 2 into 0 goes 0 times. And so 180 is the same thing as 2 times 90. Then we have to repeat. We know that 2 is prime, so we can move on to 90. And here again, we're going to guess that 2 is divisible into 90. 2 into 9 goes 4 times. 2 times 4 is 8. Subtract 8. 9 minus 8 gives you 1. Drop the 10 down, or drop the 0 down. 2 into 10 goes 5 times. 5 times 2 is 10. Subtract, you get 0. So 2 and 45 gives you 90. All right. Now, one thing students should know is that any number ending in a 5 or a 0 is divisible by 5. So I know, I don't have to guess. 45 is divisible by 5. I just know it. But if I did want to check this, I could, of course, do long division. Now, everybody should know from the multiplication table that 5 times 9 gives you 45. Okay? And then 3 and 3 gives you 9. So we have arrived at a factor tree diagram for 180. Next, if we want to find the GCF of 180 and 150, we would list out the factors of 150. And here as well, 2 will divide 150. 2 goes into 150, should go 75 times, but we can go ahead and check that. 2 into 15 goes 7 times. 7 times 2 is 14. Subtract. 2 into 10 goes 2 times. 2 times 2 is 4. I'm sorry, 2 into 10, rather, goes 5 times. 5 times 2 gives you 10. There we are. Subtract gets you 0. All right. Now, 75 is divisible by 5, but it's also divisible by 25. If you remember counting change, there are 3 quarters in 75 cents. So let's go ahead and use that fact right now. And of course, 5 times 5 gives you 25. And so now that we've arrived at all of our prime factors, 2 is prime, 3 is prime, 5 is prime, we can stop. What we will now do in order to locate our GCF is we will write out our prime factorization. 180 we said was the same thing as 2 times 2 times 5 times 3 times 3. And we said that 150 is the same thing as 2 times 5 times 5 times 3. Okay. So now we are going to locate the GCF. So just as before, we're going to cross out numbers that are in common or factors that are in common. Since we have a 2 in common between 180 and 150, I will cross out one set of 2. I also see that I have a 5 in common between 180 and 150, and I see that I have a set of 3 in common with 180 and 150. Now, each time that I cross out one set of numbers, I'm going to write that number down exactly once, and I'm going to line all of these numbers up such that they're being multiplied together. 2 times 5 gives me 10. 10 times 3 gives me 30. It turns out that 30 will be the GCF of 180 and 150. And we can prove this to ourselves by going to the side of our page and dividing 30 into 180. 30 into 180 should go 6 times. And then 30 into 150 should go 5 times. You guys can do it on your own time if you wish. But 30 is, in fact, the greatest number which will divide 180 and 150. And I hope that you can see that I've given an argument for how we can locate this greatest common factor by first listing out the prime numbers using a factor tree diagram, and then crossing out the prime number multiples that are in common between each of the numbers we want to locate the GCF of. All right, I'll give one last example. Suppose we want to find the GCF of 248 and 344. Here again, we're going to just start with one of the numbers. And what we want to do is we want to find a value that will divide 248. 248's even, so why not just divide it by 2? Don't make your life harder than it has to be. Don't have to guess, oh, is it a 4? Is it a 10? Is it this? Is it that? No, guys. I'm just going to do it the easiest way, okay? There's 1,000 different ways to do this, but, if all else is equal, we'll just do it the easiest way possible. So 2 goes into 2 one time. 1 times 2 is 2. Subtract, could get 0. Drop your 4 down. 2 into 4 goes 2 times. 2 times 4. I'm sorry, 2 times 2 is 4. You get 0. Drop your 8 down. 2 into 8 goes 4 times. And you know now that 2 times 124 gives you 248. All right. So now we're going to divide 124 by some value. And we're going to keep doing this until we arrive at all of the prime factors. Here again, 124 is even, so we'll divide it by 2. And this might not be the most efficient way of going about doing this problem, but it is an effective way. 2 will go into 62 31 times, and we should be done because 31 will in fact be a prime number. Now we will start on 344. And since 344 is even, we'll go ahead and divide 2 into 344 to see what the other factor happens to be. So 2 goes 1 time into 3, we'll subtract, drop our 4 down, 2 into 14 goes 7 times. Drop our 4 down, 2 into 4 goes 2 times, and we find that 172 times 2 gives you 344. Since 172 is even, we'll just keep doing what works best. We're going to divide 2 into 172. 2 into 17 goes 8 times. 8 times 2 is 16. Subtract, you get 1. Drop your 2 down. 2 into 12 goes 6 times. 6 times 2 gets you 12, and you get 0. All right, so 2 times 86 will give you that 172. Now we're going to divide 2 into 86. 2 goes into 8 4 times. 2 goes into 6 3 times. So this should be 43. And here we are. This will be our prime factorization of 344. Take a moment to check my math, but when you're satisfied, go ahead and we'll give ourselves a little bit more space. We're going to write out our prime factors as a sequence of numbers all multiplied together. So you should have 248 is the same thing as 2 times 2 times 2 times 31. And 344 is the same thing as 2 times 2 times 2 times 43. Now, if you want to locate that GCF, all you got to do, you're almost there. You cross out the terms that are in common. You write them down once. We got one set of 2's in common, 2 sets of 2's, 3 sets of 2's. 2 times 2 is 4, times 2 gives you 8. Your GCF will be 8. And that is all you have to do in order to find a GCF. I will see you guys in the next video. Bye-bye.